Thank you so much, Jack, and everyone for being here at 9 in the morning. I've had so much fun learning about disks and planet formation in disks from all of you. So now I'm here to turn the tables a little bit and tell you what we can learn about planet formation by studying the final dead and dying outcomes of planet formation, including our own Earth, which is itself a fossil of planet formation. To set the stage a bit, we have a lot of exoplanets from which we can do statistics. Jesse Christensen motivated this earlier in the week, but I'd like to reiterate the cumulative exoplanet discoveries are pretty profound. Back in 1995, 30 years ago, was the discovery of the first extrasolar planet, which won a Nobel Prize. Another important milestone here is my first KITP conference a decade ago. It was fun. That's why I keep coming back. Thank you for having me. You might notice that around the time of that conference, something really interesting happened with an explosion of new planet discoveries. And those are thanks to the NASA Kepler mission. This is a mission that was designed to study the statistics of exoplanets. And from its design specs, it was capable of finding Earth-sized planets in Earth-like orbits. Now, the secret to Kepler's sensitivity to Earth analogs was its survey design. Kepler continuously stared at 150,000 stars in this lovely patch of the Milky Way for 4 years. And by staring without blinking at them, it was sensitive to the transits of Earth-like planets, which have an orbital period of a year, and could perhaps capture 3 or maybe 4 such transits for Earth analogs, enabling planet detection. The main takeaway message from the Kepler mission was that small planets are abundant. I am showing here one of the very last planet candidate catalogs to come out of Kepler, with over 4,000 small planet candidates all transiting their stars. This plot shows planet size versus orbital period, and I hope you notice right away that the majority of the dots on this plot are between the sizes of Earth and Neptune, which of course is a size that we do not have represented in our solar system. Now, as promised, Kepler was looking for planets in this pink box, roughly the size and orbit of Earth. And you might notice that the top left corner of this box is more populated than the lower right corner. Now, it's not that planets are more common in the top left than the lower right. That's just an effect of our detection biases. It's easier to find large planets closer to their stars with the transit method. Fortunately, we can do injection recovery on the Kepler light curves to characterize how many planets of various sizes and orbits we tend to miss. And so this kind of work has been ongoing for a long time. And there was a watershed paper a little over a decade ago that announced that 1 in 5 sun-like stars has an Earth-sized planet in an Earth-like orbit. And this is that same plot with the red dots representing planets and the green squares representing the completeness-corrected planet occurrence as a function of size and orbital period. This was a really profound result. And it has held up over time. There are a lot of other studies that have reproduced this result within a factor of 2. For a review of those results, you can see Bryson et al. 2021 and references therein. So the takeaway is that approximately 1 in 5 sun-like stars has an Earth-like planet. And if we do some basic math, we get that there are 17 billion Earth-like planets in our galaxy. It's a lot of Earths. But our science is not done. We would like to know, what are the compositions of Earth-sized exoplanets? How did they form? And could they support life? So some things that I care about that contribute to life are rocky surfaces and liquid water. Rocky surfaces are important, or so my chemistry and biochemistry friends tell me, because chemical reactions happen faster on rocky substrates than in a sort of nebulous three-dimensional region. It's just that the molecules find each other faster in a two-dimensional surface. So chemistry happens faster on rocky surfaces. That leads to the emergence of life. That's good. Liquid water is also incredibly important. Our Earth is home to many, many different species of life, including various extremophiles. Yet one thing that all of these life forms have in common is that they are based on cells that are mostly liquid water. So we have not yet found any form of life on Earth or elsewhere that uses chemistry other than liquid water. So that might be important. All right, the good news is that when it comes to exoplanets, we can actually start to measure which exoplanets have rocky surfaces. We are not yet at a stage where we can measure liquid water on exoplanets, but I hope that that's where the field goes in the next 1 or 2 decades or so. All right, so how do we find these planets with rocky surfaces, which I will also call rocky planets? We identify these planets by making 2 different types of measurements. We see the planet's transit, from which we can measure their radius. And with Doppler follow-up, or in some cases transit timing variations, we measure a dynamical mass of the planet. We can put these together to calculate the bulk density of a planet and to first order infer its composition, although this gets a little bit dicey. So let's start with the solar system. Here are the solar system planets and their bulk densities. So bulk density is represented on the y-axis, planet size on the x-axis. As you can see, the terrestrial planets are clustered on the left side of this plot, and most of them follow a line of Earth-like composition, with the notable exception of Mercury, which, as we heard yesterday, is in fact a weirdo. Over on the right side of this plot, we have our lovely planets Uranus and Neptune, which might be ice giants, although as we heard, hey, maybe they're actually methane giants, what do we know? But these are their densities and radii. So this sets the landscape for our exoplanets, and I'm going to add them now. Here are the exoplanet densities and radii. I've replaced the solar system planets with square boxes for clarity. But when I look at this distribution of exoplanets, one feature in particular jumps out at me. There is a change in slope of planet density as a function of radius. To illustrate what I mean, I'm going to show the weighted mean density as a function of radius. That's that gray line there. That's an empirical relationship from 2014. And what's going on here is that for planets that are smaller than about 1.5 times the size of Earth, density tends to increase with increasing planet size. Now, this is true for our terrestrial planets, including the Moon, Mars, Venus, and Earth, and keeps continuing among the exoplanets up to about 1.5 times the radius of Earth. However, at 1.5 Earth radii, there's this dramatic transition where the average density starts falling with increasing radius. Now, the only way to get the densities of planets to go down as you're increasing their size is if you're adding a lower density material onto them. So a very simple explanation is that the planets on the right side of this transition are gas-enveloped exoplanets. Now, they could also harbor water or methane or carbon dioxide or what have you. But remember, Uranus and Neptune have hydrogen and helium, and probably a lot of these exoplanets have large amounts of hydrogen and helium as well. So what we found is that there's this transition, and that if you want to find the rocky planets, you should really be looking at planets that are smaller than about 1.5 times the size of the Earth. And these are planets that have approximately 5 to 10 times the mass of Earth. A few years after we made this discovery, some of my colleagues and I found some nice evidence confirming it, which is that small planets cluster in two sizes that are related to planet compositions. Some of you have heard of this as the planet radius valley at 1.8 Earth radii. And what I like to point out is that that lines up with this peak in the density radius diagram. And this alignment is actually how we determined that the left peak, the small planets, are probably the rocky ones, and that the planets in the right peak are gas enveloped. So to take a step back, we can think about exoplanets that form in sort of three different rough type bins. That we can get giant planets, which are more than 50% hydrogen and helium by mass. And then we've got the small planets. Now these planets are all predominantly rock by mass, but with a major distinction, that the ones that have rocky surfaces and optically thin atmospheres are going to be 1.5 Earth radii and smaller, whereas the ones that are between 1.5 and 4 Earth radii, the so-called mini Neptunes or sub-Neptunes, if you will, have optically thick gas envelopes that obscure their rocky surfaces from radiation, meaning that even if you put a little critter on the rocky surface, you're not going to get photons to and from that critter, between that critter and our telescope. So from my point of view, the super Earths, the ones with rocky surfaces, are way more fun to investigate for signs of life. Okay, so focusing on the terrestrial planets in our solar system, right? These are the ones we have with rocky surfaces. A couple questions come to mind. One is, how did Earth get and keep its water? And why is Mars so small? So I'm going to be discussing some of my work in attempting to answer these questions. I'll warn you, I don't have definite answers yet, but I think I've got some helpful ideas. So in terms of how Earth got its water, people like to invoke delivery of water from the outer solar system by small bodies. One such small body is comets, including the example on the left, 67P. This is a gorgeous Jupiter family comet that was visited by the ESA Rosetta mission a few years ago. And comets are great and very, very water rich. But one problem is that they tend to have way more deuterium than Earth's ocean water does. And this one is like 3 times enriched compared to Earth's ocean water. Another candidate for delivering water are small asteroids. This is Bennu, a pristine near-Earth asteroid. And based on a sample return that just came back to Earth last year, analysis of material from this asteroid has determined that it contains salt water and ammonia. So that's pretty cool. So how do these small bodies that are perhaps laden with water get to the orbit of Earth? And one of the key players in this is Jupiter. During the formation of the solar system, Jupiter redistributed material. It contains 60% of the present-day angular momentum of the solar system, so it's really good at shoving things around, probably always has been. And so for me, this drives the question, what is the role of giant planets like Jupiter in the origin of exo-Earths, including their basic size, properties, like why is Mars small, why did Earth get to be Earth-sized, and also in terms of their water content. What role do giant planets have in shaping our planets and their water? To address this question, I led a very, very long survey. This is the Kepler Giant Planet Search, where my colleagues and I spent 12 years studying 63 systems, which are shown on the left. Each of these rows represents the architecture of one planetary system. The sun is somewhere off to the left, and then semi-major axis in logarithmic scale is on the x-axis. The planet sizes are, the dot sizes are scaled to the planet masses, and colors are scaled with eccentricity. You can also look at this figure in detail in the paper if you'd like to study it. Anyway, so we did this survey of all these 63 systems that are shown. They all have close-in transiting super-Earths and mini-Neptunes. And we did not know a priori which of these systems were going to have giant planets beyond 1 AU. We detected 27 non-transiting planets and stellar companions, around 20 stars, including 13 Jovian analogs. One of the things that people are trying to decipher from this survey is whether or not systems that have a transiting super-Earth or mini-Neptune are more or less likely to have a giant planet than sun-like stars in the solar neighborhood. That is the basis of ongoing work. There's a lot of argument in the literature right now, with some studies claiming a possible but weak correlation. Other studies report an anti-correlation between the occurrence of inner planets and giant planets. So there's a lot of work going on this. I'm working on it as well. One of my takeaways for you is, even if there is some correlation here, it's very weak. And it's not really what's dominating the story of small planet formation. The presence of a giant planet is not the thing that maximally sculpts the size and orbits of and occurrence of the mini-Neptunes and super-Earths that we're finding. And I hope to show you that in the next couple of slides. But there are other patterns that are emerging from this absolutely incredible data set. So if we look at the planets from the Kepler giant planet search on a mass semi-major axis diagram, we can begin to decipher some of those patterns. So one thing I'd like to emphasize is this graph spans 7 orders of magnitude in planet mass and 4 orders of magnitude in semi-major axis. So that's just a really profound parameter space to be studying. What you're seeing here, there are some boring black dots that are small. Those correspond to stars from our survey for which we did not discover a Jupiter analog. So those are just the garden variety sub-Neptunes and super-Earths where we didn't find any exterior giants. The super-Earths and sub-Neptunes for which we did find some exterior giant planet are shown as bigger circles, and they are color-coded based on the mass of the most massive object in the system, where yellow means there's a stellar mass thing, because yellow is like the sun, and then the green and blue colors correspond to lower mass companions. So right away, I noticed sample size of 2. There are a couple of systems where we found these gorgeous stellar companions at tens of AU with very high eccentricities. And those particular stars, which are shown in the upper right, those host stars are Kepler 444 and Kepler 1130. And they have very cute little transiting inner planets way down here. These guys are Mars-sized planets and Earth-sized planets. We don't necessarily have radial velocity masses for them, but the fact that they're Mars-sized means that they're not going to be more massive than Mars-massed. So what's really neat is we can connect these systems with stars to systems with planets that are very small and also very close to their stars. So my question is, did the stellar companions, which have periastron passages of sort of 5 to 10 AU, truncate their disks and stunt the baby planets, resulting in what I like to call bonsai planets, because they're small and petite and perfect? All right. On the other hand, if we look at the planets that are the Jovian planets in sort of that Jovian region and their siblings, which are color-coded the same but in that transiting sub-Neptune region, the siblings of the Jovian planets are consistent with the other sub-Neptunes in terms of their semi-major axes and their masses. So this is the evidence that I'd really like to point out for you as showing that the Jovians have not stunted the growth or enhanced the growth in terms of just the sizes or orbits, of these sub-Neptunes. So this might be evidence for leaky dust traps like we've been discussing, right? Because the little guys with the stellar companions that like actually truncated their disks did get stunted, but then the sub-Neptunes in systems with Jovians did not. All right, so another really strong result that I'd like to show you from this survey is related to the outer giant planets and the inner transiting planets. So to explain this, I have to tell you about a metric called the gap complexity, which describes how irregular the planet spacing is. In a system with totally regular spacing, the gap complexity is 0. With 1, it's more diverse. The architectures of our multi-transiting systems are shown on the right side of this plot, and they are ranked by gap complexity, with the most irregular spacing at the top. I'd like you to take a look at this, and what I'm going to do now is add on the non-transiting companions that we found. There they are. So what you can see is that long-period giant planets correlate with gaps among the transiting planets in multi-planet systems. And this is a result that my former postdoc, Matthias He, led. There's been some theory trying to explain this. This is possibly the result of secular perturbations, but I think there's a lot more work to be done to explain this striking pattern. Speaking of patterns, these important guys were really obsessed with looking for patterns in the solar system planets. Kepler with his platonic solids, Titius and Bode with their regular geometric spacing of the planets. So a few years ago, I jumped on the pattern train. I was leading a study of 909 transiting planets in 355 multi-planet systems. And all of these planet transits came from Kepler. All of their orbital periods and transit depths came from the Kepler mission. And what we did is we spent several years getting spectra with the Keck Observatory to refine the stellar properties and get precise planet radii for all of these planets. What I'm showing here is actually just a subset of the planets from our survey. These are 51 systems that have 4 or more transiting planets. And if you look carefully, you'll see that there are some patterns in the sizes and spacing of the planets, which is that planets in the same system often have similar sizes and regular orbital spacing, like peas in a pod. So if you've heard of that pattern, this is the study that it comes from. So if you look at the top here, the top is where sizes are more uniform, and the bottom is where the sizes are less uniform. So the systems near the top exemplify the pattern best. In case you're wondering, I snuck in our solar system. It's down here where the blue arrows indicate it. Most multi-planet systems from Kepler, 80% of them, have more uniform sizes than our 4 terrestrial planets do. This was not predicted by classic formation theories, with an asterisk for actually some of Jack Lissauer's early papers where he made peas in a pod and then destroyed them with giant impacts. So we might have to change planet formation theory to reproduce these observations. And Andre's talk yesterday gave a beautiful example of how we can do that by forming a characteristic sized planet in a ring. So I'm going to be a little retro for a moment and bring back a really cool idea. So Sean Raymond and others here have worked a lot on the grand tack, which is this intricate dance that Jupiter and Saturn do during the early solar system. And this gorgeous review figure has, you might notice it at time equals 0, a whole bunch of similarly sized and regularly spaced protoplanets, kind of like peas in a pod, that then get destroyed by Jupiter and Saturn. So there was this idea like a decade ago called the grand attack, that Jupiter and Saturn destroy an early generation of peas in a pod in our own solar system when they do the grand tack. So I will leave out my summary because I'm told to stop talking. All my take-home points are here, and I'm looking forward to your questions.
thank you very much, Lauren, for an excellent introduction. I'm going to just make one point that is fully consistent with what Lauren said, but she talked about Kepler planets and Kepler planet candidates. If you study things like what she did in her detailed radial velocity, she uses Kepler planets. When she goes any statistical stuff, planet candidates, not planets, because the verification as planets is extremely biased in non-reproducible manners.
Jayan Bae, University of Florida. Thank you for this very nice talk. I have a question for your 2024 plot where you showed all different exoplanets and you talk about Jupiter mass planet. Can you go to that plot?
This one or
no, the previous one. Yeah, this one. So you said there's probably very weak, if there's any relation between the presence of Jovian planets and the inner planets. Mm-hmm. So I can kind of see that looking at other systems. But if you look at the two most massive ones, like the orange ball and yellow ball.
Those are stars.
Oh, those are stars?
Yeah, well, I cheated. Those are stars.
Okay.
Those are my bonsai planets.
I see. Okay.
Good eye. I'm glad you saw it.
Yeah, because I noticed that they have very little dots in the inner disk. Okay, I didn't read the numbers.
I know, they're so cute, right? That's why they're bonsai planets. But yes, the orange, they're 220 Jupiter masses and 628. This is actually a binary star in itself. It's like a triple system, but I didn't want to represent that here. That was too complicated. But those are stars. Yeah, all the other dots on this plot are like 10 Jupiter masses and smaller.
Okay, yeah, thanks.
Were those stars something that you found in your survey?
Kind of. We already knew about these stars. They're actually 1 arcsecond away and visible from the primary. And so there's also beautiful studies with direct imaging measuring the astrometry of that binary pair and its relation to the primary. Yeah, I'll take Ruth's question.
Ruth? Yes.
Ruth Mary Clay, UC Santa Cruz. I was actually going to ask you to talk a little bit about the selection effects associated with the bonsai planets. Are things that size equivalently easy to find around the around the single stars, and also did the Kepler source list try to remove binary stars like that?
Okay, yeah, that's a good question. Yeah, so I guess this star, we did not know about it when we started our survey at all. We found that in the radial velocities. Yeah, because it just happened to be going through periastron passage when we did our survey. So I guess in terms of our selection effects, we selected for stars that are radial velocity follow-upable. So they are temperatures less than 6,300 Kelvin, brighter than about magnitude 13.5. And then in terms of the planets, a criterion that I made was that each system in our survey had to have at least one sub-Neptune interior to 100 days. So that could be a bonsai planetary system, that could be more garden variety sub-Neptunes. I think to really continue studying the bonsai planets, we would need to do a dedicated survey where we pre-select for architectures like that are the cute little planets. A lot of them are going to be around fainter stars than are comfortable for me, but we would do it and have to go get RV follow-up of them for a long time to see which of them, if any, have these stars.
Do their radii have bigger uncertainties because of the double star?
No.
No. Okay, thanks.
Sean?
Sean Raymond, University of Bordeaux. Cool talk. This is really cool stuff. Question. So if I understood right, the systems from this survey that don't have outer companions, they must have, what, low gap complexity? Mm-hmm. And do they have anything else in common that separates them from the other ones?
Oh, yeah, good question. Yeah, so going back to, that's the wrong way. Yeah. So the ones that have the giant planets tend to have high gap complexity among their multiple inner transiting planets. Now, there were some systems where we found a giant planet, but there was only like 1 or 2 transiting inner planets, and you can't measure a gap complexity in a system like that. So I don't know what to tell you about those. We also looked for patterns. We basically repeated this exercise, but instead of sorting by gap complexity, we sorted by things like mass partitioning and I forget what else we tested a bunch of the other typical architecture metrics, and they were all really boring. It was all non-detections. This was the only detection. And I actually would have expected that giant planets might enhance mass irregularity among the transiting planets, particularly if they drive more giant impacts, which results in stochastic mass doubling. But we didn't see that.
Man Hoy?
Man Hoy Lee, the University of Hong Kong. Back to the bonsai planets. Are there systems like those without giant planets or stellar companions?
Yeah, good question. So you can see here there's a couple black dots sprinkled in the lower left, where we apparently had those systems with those small planets in our survey, but did not find a star or giant planet around them. I think it would be interesting to do more follow-up of them. I guess the other thing to keep in mind is the stars here have semi-major axes of like 10 to 50 AU. Those are really long orbital periods, and so unless you are lucky in sampling near periastron passage, you might just miss the stellar companion.
No, Lee is next.
Is there some obvious relationship between gap complexity and resonances or near resonance structure?
Oh, that's a really good question. I think Matthias, he was working with Jack on a paper related to that at some point. My recollection is that there was nothing obvious.
Yeah, resonance, very large gaps you wouldn't see in resonance systems, but aside from that, I don't know if there's anything obvious. But please identify yourself, at least the first time within a session that you...
Bennett Skinner, McMaster University. When looking at gap complexity, there's a really clear striking pattern of having more Jupiter outer companions, but it's not 100%. So in the systems in which you don't detect a Jupiter outer mass companion, do you suspect that there's just an as yet undetected Jupiter mass companion, or do you have an alternative explanation for that gap complexity?
That's a really good question. So for all of these systems, I published a mass upper limit based on the non-detection of radial velocity trends in the system, which is kind of a loose upper limit. I was just telling Jack the other day, I'm actually working on detailed injection recovery into the RVs of these to put mass upper limits as a function of orbital period for all of these. So when I'm done with that, that might be useful toward answering that question. I do also want to answer your question from this, like a sideways angle a bit, and just point out here that, like, for me as an observer, I love things that are predictive. So if I see, a system has a gap complexity of like 0.004 or like something way down here, I can expect it's not going to have a giant planet. Like none of those do. And it's only once you start getting to gap complexities of kind of like 0.3 or so among the inner transiting multi-planet systems that then becomes a strong, but you're right, not perfect predictor, because for some of these we didn't find a giant planet. But still, for like more than 50% of them, we did. Whereas the a priori occurrence of these giant planets is like 15%.
Thank you.
Richard, last question.
Richard Nelson, Queen Mary, University of London. Thanks for a very nice talk. One might think that if you have disturbance of the outer giant planet systems through, for example, dynamical instability, you might also disturb the inner system. Perhaps changing the mutual inclination. So I wonder if there's any evidence for multiplicity variations correlating, for example, with the eccentricities of the outer giants at all. Do you see any evidence that the outer giants have sort of, even if they haven't destabilized the inner systems, have they excited any mutual inclinations and changed the observed multiplicity, even if the intrinsic multiplicity hasn't changed itself?
That's a super good question. So I definitely encourage you to check out this paper by Joseph Livesi and Juliette Becker, where they actually explain the gap complexity increase as basically secular perturbations kicking one of the kids up in inclination.
So it's not shifting things radially.
Yeah. However, a sad thing about our survey is we only got 13 Jovians. Only a handful of them are actually exterior to multi-planet systems. And so when you try to like divide them between the high multiplicity or the low and the high eccentricity and the low. We're in small number statistics quagmires.
Okay, thank you very much.
Okay, so let's thank Lauren.